In measure theory, the Lebesgue measure, named after French mathematician Henri Lebesgue, is the standard way of assigning a measure to subsets of n-dimensional Euclidean space. For n equals 1, 2, or 3, it coincides with the standard measure of length, area, or volume. In general, it is also called n-dimensional volume, n-volume, or simply volume. It is used throughout real analysis, in particular to define Lebesgue integration. Sets that can be assigned a Lebesgue measure are called Lebesgue measurable. The measure of the Lebesgue measurable set A is denoted by lambda. Henri Lebesgue described this measure in the year 1901, followed the next year by his description of the Lebesgue integral. Both were published as part of his dissertation in 1902. The Lebesgue measure is often denoted dx, but this should not be confused with the distinct notion of a volume form. Definition: given a subset, with the length of an interval given by, the Lebesgue outer measure is defined as, the Lebesgue measure of E is given by its Lebesgue outer measure if, for every intuition. The first part of the definition states that the subset of the real numbers is reduced to its outer measure by coverage by sets of intervals. Each of these sets of intervals covers in the sense that when the intervals are combined together by union, they contain the total length of any covering interval set can easily overestimate the measure of because is a subset of the union of the intervals, and so the intervals may include points which are not in. The Lebesgue outer measure emerges as the greatest lower bound of the lengths from among all possible such sets. Intuitively, it is the total length of those interval sets which fit most tightly and do not overlap that characterizes the Lebesgue outer measure. Whether this outer measure translates to the Lebesgue measure proper depends on an additional condition. This condition is tested by taking subsets of the real numbers using as an instrument to split into two partitions, the part of which intersects with and the remaining part of which is not in the set difference of n. These partitions are subject to the outer measure. If for all possible such subsets of the real numbers, the partitions are cut apart by have outer measures which add up to the outer measure of, then the outer Lebesgue measure of gives its Lebesgue measure. Intuitively, this condition means that the set must not have some curious properties which causes a discrepancy in the measure of another set when is used as a mask to clip that set, hinting at the existence of sets for which the Lebesgue outer measure does not give the Lebesgue measure. Examples: any closed interval a, b of real numbers is Lebesgue measurable, and its Lebesgue measure is the length b minus a. The open interval has the same measure, since the difference between the two sets consists only of the endpoints a and b and has measure 0. Any Cartesian product of intervals a, b, and c, d is Lebesgue measurable, and its Lebesgue measure is the area of the corresponding rectangle. Moreover, every Borel set is Lebesgue measurable. However, there are Lebesgue measurable sets which are not Borel sets. Any countable set of real numbers has Lebesgue measure 0. In particular, the Lebesgue measure of the set of rational numbers is 0, although the set is dense in R. The Cantor set is an example of an uncountable set that has Lebesgue measure 0. If the axiom of determinacy holds, then all sets of reals are Lebesgue measurable. Determinacy is, however, not compatible with the axiom of choice. Vitali sets are examples of sets that are not measurable with respect to the Lebesgue measure. Their existence relies on the axiom of choice. Properties: the Lebesgue measure on Rn has the following properties. If A is a Cartesian product of intervals I1 times I2 times n, then A is Lebesgue measurable, and here I denotes the length of the interval I. If A is a disjoint union of countably many disjoint Lebesgue measurable sets, then A is itself Lebesgue measurable and lambda is equal to the sum of the measures of the involved measurable sets. If A is Lebesgue measurable, then so is its complement. lambda 0 for every Lebesgue measurable set A. If A and B are Lebesgue measurable and A is a subset of B, then lambda countable unions and intersections of Lebesgue measurable sets are Lebesgue measurable. If A is an open or closed subset of Rn, then A is Lebesgue measurable. If A is a Lebesgue measurable set, then it is approximately open and approximately closed in the sense of Lebesgue measure. A Lebesgue measurable set can be squeezed between a containing open set and a contained closed set. I.e., if A is Lebesgue measurable, then for every positive epsilon there exists an open set G and a closed set F such that GAF and lambda less than epsilon and lambda less than epsilon. A Lebesgue measurable set can be squeezed between a containing G delta set and a contained F sigma set. I.e., if A is Lebesgue measurable, then there exist a G delta set G and an F sigma set F such that GAF and lambda equals 0. Lebesgue measure is both locally finite and irregular, and so it is a radon measure. Lebesgue measure is strictly positive on non-empty open sets, and so its support is the whole of Rn. If A is a Lebesgue measurable set with lambda equals 0, then every subset of A is also a null set. F40 or I, every subset of A is measurable. If A is Lebesgue measurable and X is an element of Rn, then the translation of A by X, defined by A plus X equals A plus X. A is also Lebesgue measurable and has the same measure as A. If A is Lebesgue measurable, then the dilation of by defined by is also Lebesgue measurable and has measure. More generally, if T is a linear transformation and A is a measurable subset of Rn, then T is also Lebesgue measurable and has the measure. All the above may be succinctly summarized as follows. The Lebesgue measurable sets form a sigma algebra containing all products of intervals, and lambda is the unique complete translation invariant measure on that sigma algebra, with the Lebesgue measure also has the property of being sigma finite. Null sets. A subset of Rn is a null set if, for every epsilon greater than 0, it can be covered with countably many products of n intervals whose total volume is at most epsilon. All countable sets are null sets. If a subset of Rn has Hausdorff dimension less than n, then it is a null set with respect to n-dimensional Lebesgue measure. Here Hausdorff dimension is relative to the Euclidean metric on Rn. On the other hand, a set may have topological dimension less than n and have positive n-dimensional Lebesgue measure. An example of this is the Smith-Volterra Cantor set, which has topological dimension 0 yet has positive one-dimensional Lebesgue measure. In order to show that a given set A is Lebesgue measurable, one usually tries to find a nicer set B which differs from A only by a null set is a null set, and then show that B can be generated using countable unions and intersections from open or closed sets. Construction of the Lebesgue measure. The modern construction of the Lebesgue measure is an application of Carathéodory's extension theorem. It proceeds as follows. Fix N. A box in Rn is a set of the form whereby I, and the product symbol here represents a Cartesian product. The volume of this box is defined to be for any subset A of Rn. We can define its outer measure lambda * by. We then define the set A to be Lebesgue measurable if for every subset S of Rn, these Lebesgue measurable sets form a sigma algebra, and the Lebesgue measure is defined by lambda equals lambda * for any Lebesgue measurable set A. The existence of sets that are not Lebesgue measurable is a consequence of a certain set theoretical axiom, the axiom of choice, which is independent from many of the conventional systems of axioms for set theory. The Vitali Theorem, which follows from the axiom, states that there exist subsets of R that are not Lebesgue measurable. In 1970, Robert M. Solovay showed that the existence of sets that are not Lebesgue measurable is not provable within the framework of Zermelo-Fraenkel set theory in the absence of the axiom of choice. Relation to other measures. The Borel measure agrees with the Lebesgue measure on those sets for which it is defined. However, there are many more Lebesgue measurable sets than there are Borel measurable sets. The Borel measure is translation invariant, but not complete. The Ha measure can be defined on any locally compact group and is a generalization of the Lebesgue measure. The Hausdorff measure is a generalization of the Lebesgue measure that is useful for measuring the subsets of Rn of lower dimensions than n, like submanifolds, for example, surfaces or curves in R-cubed and fractal sets. The Hausdorff measure is not to be confused with the notion of Hausdorff dimension. It can be shown that there is no infinite dimensional analog of Lebesgue measure.